So today, I'm going to discuss electromagnetic radiation, more commonly known as light. Now, light can be thought of as a wave. As such, I thought it would be a good idea to discuss a few properties of waves. Now, the tall points are known as peaks, while the low points are known as troughs. And it is also typically a good idea to identify the center of a wave using a center line. Now, there are several things we can measure on waves, one of which being the amplitude, which is the distance from a peak to the center line. Or from the center line to a trough, they're all the same distance. Now, amplitude determines the intensity of light, which is how bright a particular wave will be. Now, another thing we can measure is frequency, which is how long it takes to complete one full cycle. So, light moves at a certain velocity, and what we do is we pick a specific point in space and time how long it takes one full cycle of light to pass by that point, and that will give us frequency, which will also tell us the type of light that we have. So it'll tell us if we have red light, or blue light, or radio waves, or X-rays, or even infrared. Now, due to the way that frequency is measured, it is given the units of per second, more commonly known as hertz, which is abbreviated Hz. And it is also assigned the Greek letter nu for its variable. Now, this looks kind of like the letter V, but there is a slight difference, so just be careful. Now, one other thing we can measure is wavelength, which is the distance from one peak to the next peak over, or from one trough to the next trough. Really, we can use any point on a wave, it's just the length of one full cycle. Now, wavelength is usually measured in meters. Unless we're working with visible light, then it is often measured in nanometers, which is just equal to 10 to the negative 9th meters. The reason for this is visible light has rather short wavelengths, so using nanometers makes the numbers look a lot nicer. Wavelength is also given the Greek letter lambda for its variable, which looks kind of like this upside down y. Now, wavelength can be used to determine the type of light, but only when light moves through one medium. If light changes the medium that it's traveling through, then the wavelength changes, and I'll get more into detail on that later. Now, light is a standing wave, which means that as it's moving, the peaks and troughs appear to just be going up and down. Now, this is opposed to the other type of wave movement that you might see in oceans, for example, where the peaks and troughs appear to actually be moving forward. Now, due to the nature of standing waves, the center points, as indicated by where the wave intersects the center line, are stationary. They do not move. These are referred to as nodes. Now, another good thing to discuss would be when waves collide. Now, one possible outcome is constructive interference. This is where the peaks of one wave intersect with the peaks of another wave, and the troughs of the first wave intersect with the troughs of the second wave, and you get a larger waves. The two waves build off of each other and create one with a larger amplitude. Now, then the other possible outcome is destructive interference, where the peaks of one wave intersect with the troughs of the other wave. Now, this causes a wave with a smaller amplitude. Now, if the amplitudes of the two colliding waves happen to be equal, then the two waves will actually completely cancel each other out, creating an area with no light where the two waves collided. Aside from being a standing wave, light has been shown to be made of oscillating electric and magnetic fields that are at right angles to each other, and that intersect at their nodes. So this is a general idea of what light would look like. Now, thanks to Maxwell's equations, which deal with electricity and magnetism, as well as contributions from a few other scientists, it has been shown that, in a vacuum, light moves at a constant 299,792,458 meters per second, which is often just abbreviated with the constant c. Now, we can actually relate wavelength and frequency to the velocity of light, because wavelength is the length of one full cycle, and frequency is how long it takes one full cycle to complete. So, if we multiply length in meters by per time in per seconds, we get length per time, or velocity, in meters per second. As such, lambda times nu equals c in a vacuum. Because, well, this is the absolute maximum speed that the fastest anything can go ever, no matter how inconvenient it is with space travel, light can actually go slower than that. Take, for example, light in the atmosphere. All of the particles in the atmosphere actually slow down light a little bit. Now, when this happens, frequency remains constant, because the electric and magnetic fields have to remain lined up. It gets fairly complicated. Point is, frequency is constant for a particular type of light, which means that when velocity changes, wavelength must change, which is what I hinted to earlier. Now, while wavelength and velocity do decrease somewhat, these changes are very small to the point of being negligible. So in general, we can say that light moves at the speed of light, as it were. Now, we can actually determine the energy of a wave of light using the equation E equals h times nu, where E is, of course, energy, nu is frequency, and h is Planck's constant, which has the value of 6.626 times 10 to the negative 34th joule seconds. Now, if we're only dealing with a few waves of light, then a joule is kind of a big unit to be measuring energy in. So, there's another form of Planck's constant, which is equal to 4.135 times 10 to the negative 15th electron volt seconds, with the electron volt being just another way to measure energy, albeit in smaller increments. Now, given our earlier equation for velocity, which was lambda times nu equals c, we can actually manipulate our energy equation so we can use wavelength instead of frequency in it. And that would look like E equals Planck's constant times the speed of light in a vacuum over wavelength. You may not realize it, but the way we calculate energy that I just described doesn't actually make any sense when light is considered a wave. For normal waves, amplitude determines energy. However, for light, amplitude determines intensity, while wavelength and frequency determine energy. This discrepancy leads us to the double slit experiment. The premise of this is that we have two very thin, very close together slits that we then shine a beam of uniform wavelength light through, i.e. a laser. Now, on the other side of these slits, we have a special screen that will indicate where light hits it. Now, when we do this experiment and don't look at it, we find these alternating bright and dark bands. This interference pattern, as it is known, is expected for waves. The bright bands are areas of constructive interference, while the dark bands have no interference, making them look comparatively dim. The reason we get such a pattern is that when the laser hits the slits, these slits split it up, essentially creating two new sources. And as you can see, these sources intersect, creating the areas of constructive interference. Now, if we do this experiment again, but observe it this time, well, then we find these two solid bands. This would be expected if light were a particle. It would just shoot right through the slits and hit the screen at only two spots. For this reason, we know that light is both a wave and a particle. Now that we know light is both a wave and a particle, this brings up the question, how? Well, scientists have determined that light acts as a collection of particles that move as a wave. So essentially the answer to the question, how is light a wave and a particle, is because it's both. Kind of cyclic reasoning, but this is quite the conundrum in physics, and even discovering wave-particle duality itself is incredible. On the plus side, we can answer why observing the double-slit experiment changes its outcome. So, in the double-slit experiment, we're testing light, which also happens to be what we use to watch the experiment. The analogy that I was given is that observing light with light is like trying to find the location of a basketball using another basketball. Sure, you'll figure out where it is, but you'll change what happens to the basketball by finding it. This is known as the observer effect, which is different than the uncertainty principle. The uncertainty principle, which states that we can't know both the position and momentum of a particle, is just an inherent property of waves. It will exist even if we don't watch it. Getting back on track, larger particles do exhibit wave-particle duality. It's just that their wavelengths are so small that they're negligible. And by larger particles, we mean protons and neutrons. In fact, the theories start to break down for anything greater than bacteria. Unfortunately, we can't currently test whether such large objects do have wave-particle duality. Now that we've sort of explained the seeming paradox of wave-particle duality, we should probably discuss the particulate form of light. Light particles are known as photons, which you've probably heard of. These are actually the force-carrying particles for the electromagnetic force. So this means that they are the reason charged objects interact with each other. However, photons themselves have no charge. They only transmit it. Okay, how about mass? Most particles have mass. Well, photons are also massless. But they do have momentum. Now, if you're familiar with momentum, then you probably know that the algebraic way to calculate it is P equals mass times velocity. So this seems like yet another paradox with light. Luckily, we can bring in what is probably the most famous equation in history. E equals mc squared. Squared plus momentum times the speed of light squared, and energy should be squared as well. This is the actual form of Einstein's equation. Most people just forget this other part. Now, don't worry, E equals mc squared is still accurate, but only when the particles aren't moving. When they are moving, as is the case with light, the energy equation forms a sort of right triangle, with each of these squared components forming a side of said right triangle. Now, as I've already mentioned, the mass of a photon is 0, so we can just cross this out, and, doing a bit of manipulation, we find that momentum is equal to energy divided by the speed of light. And, as I've already shown, light does have energy and velocity. There is also a correction to be made for gravity. Gravity doesn't just occur between objects with mass. It actually occurs between objects with energy and momentum. Now, objects with mass have both of these, so they are unchanged, but this does mean that massless objects, like light, are affected by gravity, and this has been observed. Going back to this energy equation, we can relate wavelength, and I guess also frequency, to momentum. Using our previously discussed energy equation, we can replace E with h times c over lambda. The c's cancel, and we are left with momentum equals Planck's constant over wavelength. Now that we've discussed some properties of both the wave and particulate form of light, we should see how light is formed in the first place. First, a bit about atoms. Atoms have energy levels, which are rigidly defined distances where electrons can reside. Also, as a bit of a tangent, electrons do not have a determined path in the atom. It is more of a cloud of possible locations where the electrons could be. However, for the sake of this example, we're going to pretend that we can find an electron at a single point. Now, when an atom gets excess energy, be it from a chemical reaction or some other photon striking it, the electron will be excited to a higher energy level. This is unnatural. Electrons want to be as close to the nucleus as possible. So, the electron will fall back to its original energy level. When this happens, energy is released in the form of photons. In fact, a photon is really just a packet of a certain amount of energy. Due to the rigidness of energy levels, photons from certain energy level drops will have a specific energy, and by extension, a certain frequency. In fact, the type of light we get is entirely dependent on the energy level drop of the electron. So far, we've connected photons to wavelength and frequency through energy. But what about amplitude? Well, amplitude, which determines intensity, simply translates to the number of photons we have. Nothing too complicated. But, nevertheless, hope you enjoyed it, hope you learned something, and see ya.